All right, welcome everyone. So today we're going to do a bit of an introduction to our lab that we'll be running today, which is we're up this week, which is on extractions. Okay, so these are commonly used processes, both in organic chemistry lab, but also commonly used in everyday life. As you sort of will see through the lab that we're going to run, we're essentially going to start off by making essentially coffee, which is essentially extracting organic compounds from a solid ground coffee into water, which is going to act as our solvent in that case. That's, of course, a very commonly used process. It's the basis of, a huge industry, the tea, the coffee, the beverage industry is based on a lot of these principles. We'll be going through some of that, as well as some more organic, specific types of extractions, which are also used on an industrial scale. Okay, so kind of as we mentioned, extraction is a term we use for moving or transferring molecules or a compound between different phases. Okay, so these are different phases. Sometimes they're states of matter, and sometimes they're the same state of matter, but two different versions of it. We'll see examples of both. Okay. Um, so in organic chemistry, extraction is commonly used to purify and to separate. Okay, so the one example that we sort of started with is if you prepare a cup of tea or coffee, that is a solid liquid extraction, right? So if you imagine your leaves of tea or your grounds of coffee, those are effectively solids, but they contain organic compounds that are at least partially soluble in the actual solvent, which in the case of beverages is going to be water. Okay, so in that case, soluble compounds are separated from insoluble compounds by putting it in a solvent. And that's a principle of essentially making tea or coffee. Okay, so that's where your two phases are also distinct states of matter. One of them is a solid, such as your leaves of tea or your grounds of coffee. This is also commonly used, for instance, in organic chemistry, if we have a compound that is insoluble, but it contains some amount of compound that we are interested in there, we can actually filter and essentially extract out the soluble components and leave by the insoluble organic compounds, also in the context of organic lab. Okay, so that's what we mean by solid liquid extraction. One of the phases is solid, one of the phases is liquid. Okay, liquid extraction, on the other hand, okay, have to pick two liquids which are not miscible, right? So kind of going back to that old principle that oil and water do not mix, right? So no matter how much you try, if you take some kind of oil, so olive oil, or you take canola oil, or butter, or any other oil type product, and you try to mix it with water, it just won't mix, okay, because they're immiscible, okay. In that case, there we have two liquid phases that are distinct, an oil phase and a water phase, but they're not miscible. They're both liquids. Okay. In the context of organic chemistry, we generally will not use oils as our solvents because they're not very homogeneous, right? They can vary depending on supplier, etc. What we'll often use is the same principle of a organic and an aqueous layer, but where the organic layer is some solvent that's not miscible with water, right? So that can be things such as toluene, hexane, ethyl acetate. It can be things like dichloromethane or chloroform. These are all examples of organic solvents, organic liquids, which are not miscible with water. So liquid extraction really requires us to have two liquid layers that do not mix. So it wouldn't work, for instance, with something like methanol and water, those two mix, and so you can't do a liquid-liquid extraction in that case. Okay, so the two liquids have to be immiscible, and the compounds are then separated between these two immiscible liquids, so our organic layer and our aqueous layer, depending on which phase they prefer to be in. Some things that are more polar, so compounds with lots of hydrogen bonding groups, for instance, will prefer to go to the aqueous layer, and compounds that have a lot of hydrocarbon type groups or not many polar groups, those will prefer to go to the organic phase. Okay, and so that way we start off with everything in one phase, but we have multiple compounds. Some of them will be more soluble in water, some will be more soluble in the organic phase, and so we can separate them and purify it that way. Okay, so solid liquid extraction, the idea is we extract out the soluble components to liquid. The liquid-liquid extraction is a little bit trickier, and we have to think about a couple of different parameters. Okay, so for instance, it's used very commonly because it's a relatively simple way of separating compounds that are more hydrophobic or don't like water very much from compounds such as inorganics or molecules, lots of things like hydrogen bonding groups on them, which are much more soluble in water, right? So the hydrophobic things will prefer to go to the organic phase, right? So typically organic products will typically prefer to go to the organic phase, and inorganic or highly polar compounds will tend to go to the aqueous phase, right? Because they're hydrophilic. Okay, so now in the case of caffeine, right? If we present our caffeine molecule with two different phases, the caffeine molecule is sort of an organic compound. It tends to prefer the organic layer, which in the case of our lab is going to be ethyl acetate. Okay. And so we can define this as essentially being a partition coefficient, or it's effectively an equilibrium constant. It's the concentration of caffeine in the organic layer divided by the concentration of caffeine in the aqueous layer at equilibrium. And in the case of ethyl acetate water for caffeine, it's about 2, which means caffeine prefers to be in the organic layer by about a factor of 2. Okay. The other thing to keep in mind when you're considering these is it's often more efficient to do multiple smaller extractions, right? So if we're going to start off with the caffeine being in the aqueous layer, it's more efficient to do 3 times, say, 20 milliliters or 30 milliliters of ethyl acetate, and then collect the organic layers together, right? So you do a liquid-liquid extraction with, say, 25 milliliters of ethyl acetate, collect that ethyl acetate, and then present it with a new pure collection of ethyl acetate, do the liquid-liquid extraction, collect the ethyl acetate, and repeat again. That's actually a bit more efficient than if we were to do one extraction with 75, or the full amount of organic solvent. So that's just a little procedural thing. Okay, so the technique and the equipment used to do a liquid-liquid extraction, okay? So the main equipment used is what's called a separatory funnel, okay? So we have here a stopcock, okay? So this is a stopcock here. And then we have a stopper up here, okay? So the stopper just is removed, okay? So we can simply remove this, add any solvents we like once it's removed, so we can just add solvents freely into here, okay? Keeping this at the bottom closed, okay? So what we can actually do is we can essentially allow the two layers to mix in here, right? We're going to have a layer up here, layer down here. We're going to allow them to mix. And then we can actually open this stopcock and just under gravity drain out the heavier of the two first, Okay, collect that. And then after that, we can stop and then collect this second phase because it will be down the bottom there. Okay. So as we kind of mentioned, in the context of organic chemistry, we like to use relatively pure organic solvents. One of the phases will be water. We can get that in high purity. The other one is an organic solvent. Commonly, things like ethyl acetate, which is what we use in this lab, diethyl ether, methylene chloride, also called dichloromethane, chloroform, toluene, etc. These are all organic liquids. Okay, so as we kind of mentioned, this is what you can expect during your extraction. Okay. Remember, water has a density of 1 gram per milliliter, and the rule is generally organic solvents which are non-halogenated, they do not contain heavy halogens, those are up here. Okay, so they're in the top layer. They're less dense than water, so by gravity they go to the top. Okay. Whereas halogenated organic solvents such as chloroform, chlorine's heavy, so it drags it to the bottom. But in the context of this lab, we're going to be using ethyl acetate, right? So ethyl acetate is this molecule up here. Okay, just draw it in. There's the acetate. There is the ethyl group. Okay. There's no halogens there, so that's going to be in the top phase up here. And our aqueous layer is going to be down here. Okay. So our aqueous layer will be down the bottom. Okay. Our goal, if we look at this caffeine molecule, right, it's got a lot of carbons, things like that. It's got a few polar groups, but overall it doesn't have a huge number of charges or things like that. So it'll slightly prefer the organic layer. And that's why we're going to start off with it being extracted into water, same way as we would if we make a normal cup of coffee. But then we're going to extract it into the aqueous layer, so into the organic layer up here. Okay, so we'll start off caffeine in the aqueous layer, and then we will extract it. We'll move it up into the organic layer, which will be ethyl acetate. Once we do that, we can open the stopcock, drain out all of the aqueous layer, and then we can collect the organic layer. We can put the aqueous layer back in, do another extraction. That will increase our yield. Okay. So the other thing to keep in mind is when we do these liquid-liquid extractions, although ethyl acetate and water are not miscible, they're immiscible, they still have a little bit of cross-solubility, so it's not zero. So there's going to be a little bit of water that gets into our ethyl acetate. So once we remove and put to the side the vast majority of our water, we're still going to have a little bit of water that's sort of mixed in up here. And to get rid of that, we'll typically dry it with something like some kind of inorganic salt, such as in our case, it will be magnesium sulfate. Okay, so now we're going to have our pure, hopefully relatively pure caffeine in ethyl acetate. We don't actually want the solvent, so we're going to use this piece of equipment here, which is called a rotary evaporator, also called a rotovap, okay, to essentially remove the ethyl acetate solvent. And to make it easier and go under milder conditions, we're going to do it under reduced pressure, right? So that's what this hose is. This hose runs all the way down here, okay? Is the vacuum hose that puts our system under reduced pressure. We're going to put our flask right here, okay, which will contain our caffeine in ethyl acetate. Key thing is don't fill the flask more than halfway because it tends to make a bit of a mess and spill up here. Then you'll put it in this water bath, warm it up a little bit, put the system under reduced pressure, and your volatile ethyl acetate will come up here. It'll hit these coils which contain cold water, okay, running through them. It'll recondense and get collected down in this flask down here. Okay, as we continue this, we're going to continue to remove more and more and more of our ethyl acetate, and eventually we're going to get our caffeine product at the end. All right. Key thing is at the end of it, we can turn off the rotovap. It'll be rotating just to kind of help mix it. Stop the rotation, break the vacuum holding the flask here. Then we can take it off and collect our caffeine at the end and do our analysis on it. All right. So thank you, everyone, and hopefully this lab goes great for you.